Hydrogen atom 2p state. The normalized radial wave function for the 2p state of the hydrogen atom is capital R sub 2p equals 1 over square root 24a to the fifth power parentheses r exponential minus r over 2a. After we average over the angular variables, the radial probability function becomes P of R dr is R sub 2p parentheses square 4 pi r squared dr. At what value of R is P of R the probability density for the 2p state a maximum? Compare your results to the radius of the n equals 2 state in the Bohr model. Okay, so probability density function P of R is R sub 2p squared divided by 4 pi r squared. So you can see here. So this is 4 pi divided by 24 a to the fifth power, and we have r squared multiplied by r squared, r to the fourth power, e to the minus r divided by the Bohr radius a. This is equal to basically r 2p squared multiplied by 4 pi r squared. That's our probability density function as a function of r. Now, if I look at dp dr, this is first I have the r to the fourth power, so it's going to give me 4r cube exponential minus r over a, and then from the exponential I will get minus 1 over a, so I will have minus r to the fourth e to the minus r over a divided by a, and this is multiplied by the prefactor 4 pi over 24 a to the fifth power. Okay, so we have to set this equal to 0 to get the maximum probability. dp dr is equal to 0 gives me 4r cube minus r to the fourth power exponential minus r over a divided by a is equal to 0. In r cube, e to the minus r over a parentheses, I have 4 minus r over a is equal to 0. And this gives me r is equal to 4a as the highest probability radial distance. If you substitute this here, you will get a high number because you have r to the fourth power. You could substitute r equals 0, which would give you 0 probability. You can substitute infinity, which will give you also 0 probability. So this is the maximum probability answer. So 0 and infinity do not give the maximum probability. In the Bohr model, now we're supposed to compare it to the Bohr model. In the Bohr model, we have the angular momentum mvr, r cross with mv, quantized in units of h bar. And we have the centripetal force ke squared over r squared is equal to mass times the centripetal acceleration mv squared over r. If I multiply this equation with mr squared, I obtain mke squared so this is mke squared times r is going to be equal to mbr parentheses squared, which is n squared h bar squared according to Bohr postulates. So I can see that r sub n is n squared h bar squared. So it's n squared times h bar squared divided by mass times Coulomb's constant times the electron charge squared, which is n squared times the Bohr radius a. So if I have n is equal to 2, I will have R2 is equal to 4a. So that means I have an agreement with the maximum probability maximum in P sub r. Okay, so for n is equal to 2, that's the 2p state. I have r sub n, the orbital radius, is equal to 4a, and according to my quantum mechanical calculation, the most probable radius is 4a, so those two are in agreement. Now, as a remark, I want to note here that the probability density, radial probability density, is not equal to r sub 2p square, since r sub 2p square is the probability per volume, probability density per volume. Therefore, we have P of r dr is equal to r sub 2p square dv, where the differential volume is 4 pi r squared dr for a spherical shell. Okay, so in this problem, we have worried about the 2p state of hydrogen. The given normalized radial wave function is this. We found the maximum probability by looking at the probability density as a function of r, which is probability per volume multiplied by dr. So probability per volume is r2p squared, 4 pi r squared, and we take its derivative with respect to r, set it equal to 0, which has three solutions: 4a, infinite, and 0. 0 and infinite give us 0 probability, but r equals 4a gives us a positive probability, so that is the maximum extremum point. Looking at the Bohr model, angular momentum is quantized, mvr is nh bar. The centripetal force, Coulomb's constant, electron charge squared divided by r squared is mv squared over r. Multiplying both sides of this equation with mr squared, we obtain angular momentum square is equal to mke squared over multiplied by r. So the orbital radii are given by n squared times the Bohr radius. And for n is equal to 2, that's 4a, in agreement with this result. And finally, I have this remark here: the absolute psi square is the probability per volume. So we have to be careful with that when we use the radial distance as the dimension that we're worrying about.